All right, if you're gearing up for a coding interview or you just want to seriously level up your algorithm skills, you are in exactly the right place. Because over the next few minutes, we're going to completely demystify one of the most fundamental graph algorithms out there, breadth first search, or BFS for short. But let's kick things off with a classic problem. Picture this. You're standing in the middle of a huge maze. Every single corridor is the exact same length. How can you be absolutely 100% certain that you found the fastest way out? Not just any way out, but the shortest one.
Well, that right there is the exact kind of question breadth first search was designed to answer. Whenever every step you take, every edge in your graph has the same cost, BFS is your absolute best friend for finding the shortest path. It's elegant, it's efficient, and it is incredibly powerful.
Okay, so to really get BFS, we're not going to start with a bunch of code. Nope. We need a simple, powerful image that just helps the whole thing click. So let's start there. I want you to think about dropping a pebble into a perfectly still pond. You know what happens, right? You see those beautiful, expanding concentric circles? That physical phenomenon, that is the perfect mental model for how BFS explores a network. The exact spot where the pebble hits the water, that's our starting node, our source. We can think of this as layer zero. It's ground zero for our entire search. Now, that very first ripple that spreads out, it touches all the points that are exactly 1 unit away from the center. In the world of graphs, this is layer 1, all the nodes that are directly connected to our starting point. BFS explores every single one of these before it moves any further. And then, the second ripple expands from the edge of the first one. This is layer 2. BFS is super methodical. It systematically explores all the unvisited neighbors of the layer 1 nodes. It's this strict, level-by-level exploration that is the absolute core of the algorithm. It will not even think about moving to layer 3 until every single node in layer 2 has been checked. And this is what's so brilliant about it. By exploring layer by layer, the very first time we reach any given node, we have provably done it using the shortest possible path, at least in terms of the number of steps. There's just no way to get there faster, right? Because we would have had to cross fewer layers, and we already explored all of those.
So that's the idea. But how do we actually translate this ripple effect into code? The magic is in a really simple data structure that perfectly mimics this expanding wave. The engine that drives BFS is the queue.
The whole process is really methodical. We start with a queue that just has our source node in it. Then we just start a loop. Pull the first person in line, which is our current node. We look at all its neighbors. And if we haven't seen a neighbor before, we add it to the back of the line, the back of the queue. This whole first in, first out behavior is what perfectly enforces that ripple-like, level-by-level exploration. Let's just trace this on a simple path from A to D. We start by putting A in the queue. In our first step, we pull A from the front and we add its only neighbor, B, to the back. In the next step, we pull B and add its neighbor, C. You see the pattern here? The queue always holds the nodes on the current edge of our ripple, and our distance map gets built up perfectly, 1 layer at a time. It's simple, it's predictable, and it guarantees that shortest path. And that predictability, it extends to its performance, which is a huge reason why it's so popular in technical interviews. It's not just correct, it's fast. BFS has a time complexity of O of V plus E, where V is the number of vertices and E is the number of edges. This is what we call linear time. And why is that? Because in a well-implemented BFS, every single vertex is put into the queue and taken out of the queue exactly once, and every single edge is looked at exactly once. You really can't get much more efficient.
But here's a crucial detail. How you represent your graph matters a lot. For most real-world situations, graphs are what we call sparse. They have way fewer connections than the maximum possible. In those cases, an adjacency list gives you that fantastic OV plus E performance. If you use an adjacency matrix instead, you're looking at OV squared, which can be way slower on those same sparse graphs.
So, knowing all this, when should BFS be the tool you reach for? It's all about matching the problem to the algorithm's unique strengths. Knowing when to pull this tool out is so important. Unweighted shortest path is the classic case. Think of the maze, or finding degrees of separation on a social network. But it's also perfect for level-order tree traversals, for finding all the disconnected parts of a network, or even for checking if a graph is bipartite, which is a fancy way of saying you can color it with just 2 colors, without any neighbors having the same color. Now, you can't really talk about BFS without mentioning its sibling, Depth First Search, or DFS. The key difference here really boils down to the data structure. BFS uses a queue to go wide, layer by layer. DFS uses a stack, which makes it go deep, exploring one single path as far as it can possibly go before it backtracks. And this means BFS finds the shortest path, while DFS does not.
So what happens if your graph does have weights? You know, like a map, where roads have different travel times. Well, that's when you graduate from BFS to Dijkstra's algorithm. You can really just think of BFS as a special, simpler case of Dijkstra's where every single edge has a weight of 1. The moment those weights start to vary, you need the more powerful tool.
Wow, okay, we've covered a lot of ground, from that core intuition all the way to implementation and when to use it. Let's distill all of this down into the essential takeaways. Okay, well, let's lock in these key ideas. First, always remember the ripple effect. That's your intuition. Second, the queue is the engine making that ripple happen in your code. Third, its superpower is finding the shortest path in any unweighted graph. Fourth, it's incredibly fast, O of V plus E time. And finally, here's a little pro tip for you. Mark nodes as visited the moment you add them to the queue, not when you pull them out. That simple trick prevents a ton of redundant work and keeps your algorithm perfectly efficient. Now it's your turn. It's time to put this knowledge to work. A perfect next step is to go tackle the word ladder problem on a site like LeetCode. It looks like a word puzzle, but here's the secret. If you treat words as nodes and a single letter change as an edge, you'll suddenly realize it's just a shortest path problem in disguise, perfect for BFS. Give it a shot. I promise, once you solve that one, an entire class of graph problems will suddenly just click into place.